So in this lesson, we're going to define the binomial distribution, which is a very important probability distribution you'll see a lot in this class. Let's begin with an example. Suppose a basketball player makes 75% of his free throws. If he shoots three free throws, what's the probability he makes exactly 2 of those 3 shots? So when he shoots 3 shots, for each shot he could either make the shot or miss the shot. So there's 2 possible things that could happen on the first shot, 2 on the second, 2 on the third. 2 times 2 times 2 is 8. So there's 8 possible sequences of results. And there they are. Now here, a Y represents a made shot and an N represents a missed shot. So this would mean he made all 3. This would mean he missed all 3. Now there are 8 outcomes here, but since he makes 75% of his shots, these 8 outcomes are not equally likely. Here are their probabilities. For example, the chance he makes all 3 shots is 0.75 times 0.75 times 0.75, because he makes 75% of his free throws. Our question was, what's the probability he makes 2 of the 3 shots? Well, if I look at this list of outcomes, there are 3 distinct ways he could make 2 and miss 1. Those 3 right there. And each of them has the same probability, because each of them has 0.75 multiplied together twice and 0.25 once. So each of them has this probability. These are 3 disjoint ways that he could accomplish the task of making 2 out of 3. That means the probability he makes 2 out of 3 is 3 times this probability. We have to add these 3 probabilities together. And that's about 42.2%. We want to generalize this idea so we can compute the probability of making any number of shots out of any number of attempts. Before we do this, we want to be able to use this outside making a free throw. So the critical components of a situation like this are what we call a Bernoulli trial. A Bernoulli trial is a repeated random event with 2 properties. One is that it has only 2 outcomes, which we call success and failure. And there's a constant probability of success. As you repeat the trial, the chance of a success never changes. Traditionally, we represent the probability of success with the lowercase p, and therefore probability of failure is 1 minus p. So for example, in the free throw case, p was 0.75, because that was the chance of making a free throw, and chance of missing was 1 minus p, 1 minus 0.75. So let's think about Bernoulli trials. Tossing a coin is a Bernoulli trial. If we define a success as flipping a head, then the probability of success is 0.50. The coin has no memory, so that stays the same. It's always 50% chance of flipping a head. Rolling a fair die isn't a Bernoulli trial because there's 6 different outcomes. But if I roll the die and ask a yes or no question, like is the roll a 2 or a 3, then that makes it a Bernoulli trial. In general, if we have some repeatable independent random event, we can make it into a Bernoulli trial if we simply ask a yes or no question about the result. How about shooting free throws that we used in our first example? Is that a Bernoulli trial? Well, we want to assert that the probability of success is always the same. And that's reasonable as long as we don't do too many shots. If somebody's shooting a whole lot of shots, they might start getting fatigued, so the probability of success might go down, or that's practicing because they're shooting a lot of shots, so the probability of success might go up. So if we're shooting a whole lot of shots, then it wouldn't be reasonable. But just for a few shots, we could say, okay, we're going to model this using as a Bernoulli trial. We'll have a fixed probability of success of making a free throw. What if we're flipping cards from a deck? We flip them over one at a time and ask the question, is this a black card? Is this a black card? Can we use Bernoulli trials to model this? Here the answer is no. Because as I flip over cards, the chance that the next card is black is changing each time because I'm removing cards from the deck. After I flip the first 10 cards, the composition of the remaining 42 cards in the deck is different than it was at the start. So the probability of is the card being black may have changed. Since the probability of success is changing, that's not a Bernoulli trial. Last example. What if I have 1,000 people and I sample from them at random, asking some yes or no trial? Could I use Bernoulli trials to model this? Well, when I sample, I generally don't ask the same person twice. So this is analogous to flipping cards from a deck. I ask a person, I set them aside, go to the next person, I set them aside, etc. But here the deck is large. We have 1,000 people, so it's like a 1,000 card deck we're asking this yes or no question about. And the probability doesn't change much if I remove a few cards from this deck. If I've taken 2 or 3 people and asked them some yes or no question, that doesn't change the percentage of people who might say yes in the remaining population, because I've only removed 3 people out of this rather large population. So the rule of thumb we use is if I'm sampling from a finite population, I can consider the draws independent and treat them as Bernoulli trials as long as my sample size is less than 1/10 of the population. This is something we'll have to take into consideration frequently as we go forward in the course. In this case, if my sample size is less than 100, that's less than 1/10 of 1,000, so I could treat the draws as Bernoulli trials, even though technically they're not exactly. It's not unreasonable to treat them as Bernoulli trials. Okay, let's generalize our free throw example, and we're going to generate the binomial distribution formula from this. We'll take 2 steps to generalize. First, we're going to have a generic Bernoulli trial with probability of success P, rather than free throws with 75% chance of success. Let's do the trial 10 times. What's the probability of getting 7 successes, and therefore 3 failures, because we're doing 10 trials? One possible sequence of successes and failures that would give 7 successes and 3 failures is this one here. Success, success, failure, success, failure, success, 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 failure. That's 7 successes and 3 failures. So the probability of getting this particular sequence of successes and failures is p to the 7th power times 1 minus p to the 3rd power. Because remember, the chance of getting a success is p. We have 7 copies of s, so we have p to the 7th power, and then we have 1 minus p to the 3rd power for the 3 failures in this sequence. But this is the probability of just that particular sequence of successes and failures. The question is, what's the chance of getting 7 successes and 3 failures? We don't really care about the order that they happen, as long as I end up with 7 successes and 3 failures. So what I need to figure out is how many ways I could rearrange the sequence of successes and failures. So this is a formula you learn in Algebra 2 and in Pre-Calculus. It's called 10 choose 7, which is written 10C7 on calculators, and in textbooks it's written like this. It's read 10 choose 7. We're going to use this first notation because this is hard to type on a computer. 10 choose 7 is computed by doing 10 factorial divided by 7 factorial, 3 factorial. This works out to be 120. So that means there's 120 different orders I could have of successes and failures. Each of them has this probability of occurring, because there'll be 7 successes and 3 failures. So we have p to the 7th, 1 minus p to the 3rd. So that means the probability of getting 7 successes and 3 failures is 120 times this probability. So I want to put you to rest. If you're freaking out about, oh, I have to derive this formula, work with this formula a lot, you won't have to. You'll see why shortly. Let's finish our generalization. So now we're going to do repeated Bernoulli trial with probability of success p. But now we're going to do it, instead of 10 times, we're going to just do it n times. We're going to replace that specific value with a variable. And then the same thing, instead of looking for 7 successes, we're going to be looking for k successes. We're going to replace that specific value 7 with a general value k. So I want to know, what's the probability of getting k successes out of n trials of a Bernoulli trial? Before, our answer was 10 choose 7, p to the 7th times 1 minus p to the 3rd. What we've changed is we now have n trials instead of 10 and k successes instead of 7. So that means I need to replace this with n, this with k, and this is 10 minus 7, which I want to replace with n minus k. So there's our binomial distribution formula. The probability of k successes out of n trials is n choose k, p to the k, 1 minus p to the n minus k. This is the formula for the binomial distribution. Now here's the good news. I was telling you not to worry earlier. A TI-80X calculator does all of this work for you. You don't have to memorize that formula. They have a built-in function called binom PDF that computes the value using that formula, so you don't have to memorize the formula. You should focus on learning how to recognize problems that require the use of this distribution, and then remembering how to use the function on the calculator to answer it. So I'm going to do an example here using the calculator. Let me show you how the function works in the calculator. It's found in the distributions menu, where you also find norm CDF and other things. It's the 11th choice. You have to go down a ways, labeled A. You can also do distribution and just hit the letter A, and it will jump there. In the newer calculators, it spells out exactly what you need to enter. So if you do Binomial PDF, it'll bring up a menu that looks like this. So this would compute, this example I've done here, this computes the probability of getting out of 10 trials, 6 successes, if there's a 50% chance of success. For example, if I'm tossing a coin and I want to know what's the chance of getting 6 heads out of 10, this would compute that value. On the older calculators, they don't have the fancy menu, so you have to remember the order. Number of trials, probability of success on a single trial, and then the number of successes that you're looking for. So this is how you'd enter it on an older calculator. 10 is the number of trials, 50% chance of success because I'm tossing a coin, and I want to look at the probability of getting 6 successes. If you're not going to be using a TI-80X calculator, borrowing one of mine or using your own, then you should either memorize the formula and learn how to use that, or you should find a reliable online binomial distribution calculator, and there's several out there. So let's do an example. Suppose in a certain game, you roll a fair 6-sided die to determine whether or not your pieces score a hit, and each roll of a 5 or a 6 is considered a hit. Let's say you have 8 pieces attacking, so you're going to get to roll 8 dice. Remember, each die is a hit on a 5 or 6. What's the probability we score 0 hits? First, before we go to the calculator, let's recognize this problem calls for the binomial distribution. We have a repeated Bernoulli trial. We're rolling a die 8 times, and the probability of success, the probability of getting a hit in this case, is always 2 out of 6, which is 1/3. And we want to know the probability of getting a certain number of successes out of these 8 trials. This is precisely where you use the binomial distribution. Fixed number of trials, constant probability of success, and I want to say, what's the chance I get so many successes out of these 8 trials in this case? So there's 2 ways to answer this question. What's the probability we score 0 hits? One, of course, is we can use the binomial distribution. We're doing 8 trials. Chance of success is 1/3. And we want to know what's the chance of getting 0 successes, 0 hits. I run that through my calculator. It gives me 0.039, so like 3.9%. Or another way to do this one, since we're looking for 0 hits, there's only one sequence of results that gives 0 hits. 8 consecutive misses. So you'd have to have miss, 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 8 times in a row. And that's the only way that can happen. Since the chance of a miss is 2 in 3, we could compute the probability directly as 2/3 to the 8th power, because I have 8 consecutive misses. And the calculator shows that that's the same result. Next example. What's the probability we score 4 hits or 5 hits? This is pretty straightforward. This is 2 binomial probabilities added together. We've got the chance of getting 4 successes out of 8 trials, plus the chance of getting 5 successes out of 8 trials. If I ask my calculator for that, it gives out to be about 23.9%. There's the calculated work. You can't quite see the 4 or the 5 here. It got cut off because it took too much room on the screen of the calculator. Last example. In order to win a battle, you need to roll at least 2 hits. What's the probability you win the battle? Now, at least 2 hits means 2 or more. So that's 2 hits or 3 hits or 4 or 5 or 6 or 7 or 8 hits. That's a lot of binomial probabilities to calculate. It would be a hassle. There's a better way. A better way to do this, instead of calculating the probability of getting you get 2 hits or more, is to say, what's the chance you don't get at least 2 hits? So if you don't get at least 2 hits, that means you got 0 hits or you got 1 hit. And then you subtract that probability from 1, and that will tell you the chance that you do get at least 2 hits. We make sure you understand that. We're going to compute the probability we don't get at least 2 hits, which means you get 0 or 1, and then we'll subtract that from 1, and that will tell me the probability that I do get at least 2 hits. This is a lot less work because it's only 2 binomial probabilities rather than that long list of 2 through 8. Further, it's nice because we already know the probability of 0 hits. We did that in the earlier slide. So if I use my binomial probability, here's the chance of getting 1 hit out of 8. The 1 got cut off over here. And then I had to take 1 minus the chance of 0 hits, also minus the chance of getting 1 hit. And that leaves me with the chance that I get 2 or more hits, which is 80.5%.